The first part of stormwater treatment design is to increase infiltrations, because without infiltrations, there is no reduction in runoff volume, or there is no treatments. So there are a couple of ways to increase infiltrations. The first, as I said, the first function is to improve infiltrations so that you can reduce runoff volume. One way to do it is to increase hydraulic conductivity, or increase the passage of stormwater through this filter media. So when I say filter media, this is what I'm talking about. So that's the hydraulic conductivity. That's how we express K. So you know hydraulic conductivity from CE159. I'll just explain very little here. Again, why we need to improve hydraulic conductivity? First, you know that hydraulic conductivity in a system is not constant. It can change based on how much sediments or suspended sediments are deposited in the system, because they will usually clog the system. So to improve design, you wanted to start with something higher hydraulic conductivity than normally what you need. So to improve hydraulic conductivity, you have to add materials which has high hydraulic conductivity to begin with. Or you can have a pre-treatment system so that you can divert some of the sediment before it enters the system. And so those are the pre-treatment strategy or pre-treatment strategy to improve or treat first pass. For instance, for retention pond, let's say this is retention pond, and you do not want to deposit too much sediment here. To do that, what you do is you wanted to create a, let's say, pre-treatment strategy. Let's say this is the manhole or something, a big hole where you can cover that with a screen. So what it does, it allows stormwater to get in first, and then it will deposit most of the sediments, because the first pass, once the first pass is filling the system, those sediments are settled here. Then rest of the stormwater will come in. And when it does, you have already removed a lot of these sediments to begin with. So, and then you can, it's very easy to clean the system here because this is cement. So that means you can always, every year, the maintenance will be less expensive by just removing sediments here once it's filled. So this is another way to prevent clogging of the actual system. But as I said, the very first thing you want to do is increase infiltration capacity to higher than what you need, so that even you have clogging, it will still maintain its capacity, at least the minimum capacity that you need. And to do that, you have to add different materials. And here are the list of materials you can add based on hydraulic conductivity. So this right side is hydraulic conductivity K. You can notice that sand, which are most commonly used, have higher capacity. If you see over here, so what you wanted to do is use those sands. We're not going to use something that has very low infiltration capacity to begin with. And in fact, these are the reason, clay and clones are the reason why things are clogged at the first place. So you want to avoid them. So again, you have choice here, and that what you use, it depends on what's the final performance criteria. If you use too coarse sand, that means you achieve high infiltration capacity, but also you reduce the contaminant removal capacity, because if water moves so fast, it doesn't have enough time for contaminants to get removed. Now, question is, you have to also conceptually understand how hydraulic conductivity can change based on the particle size you use or the way you pack. So there are two equations you want to remember. This is empirical equations which relate hydraulic conductivity with particle size. So it says that hydraulic conductivity is related to particle size to the power 2, the square. And C is empirical constant, and that determined by experimentally or by any from the data that you receive for your system. D10 means diameter of the particles for 10% passing. Means anything below that size will constitute 10% of the raw materials. So this is all about particle size. That means as long as you have less amount of finer particles, you have high hydraulic conductivity. So another way to say is if you have D10 is high, means you have the smallest portion of particles are actually big particles, then you can think that the K is higher. Again, the reason we use D10 not D50 is because the smallest particle that determine the hydraulic conductivity, the large, because they will clog faster. The second half on the the right side of the equation determines hydraulic conductivity with porosity. So E is porosity. Typically, hydraulic conductivity decreases if you decrease porosity because you have less pore space. That means it will also have higher resistance for water to move. So this is a very famous equations, Kronj-Kármán equations. It states that hydraulic conductivity is directly proportional to the porosity Q divided by 1 minus porosity. So you should use any of those two equations to understand how your design factor is going to influence the net hydraulic conductivity of the media. So this is again, porosity can change because of packing. So you do not want to pack too much. If you pack too much, that means you are decreasing hydraulic conductivity of the materials. Second half is measurement of hydraulic conductivity.